Yeah, hi everyone. Yeah, I'm John Lee from the Department of Chemical and Material Engineering. So the topic of my presentation today is construction of an electrochemical detection system for simultaneous ultra-sensitive determination of PFAS. Yeah, so this is the outline of my presentation. So in the first part, I will talk a little bit background information about the PFAS. And then is the impedance sensor for PFAS detection and summary and acknowledgement. Okay, as we know that the PFAS are a class of man-made chemicals that have been widely used, and due to the carbon and the fluorine bond that they can, exist in our environment for a long time. And among the PFAS molecules, PFOS and PFOA are two chemicals that are mostly used and studied, and both of them material that can exist in the water for quite a long time. Yeah. And nowadays, different techniques have been used for the detection of PFAS molecules. And among them, liquid chromatography and mass spectroscopy is mostly is a frequently used technique for the detection of water contamination. And this table summarizes some examples that are using this method to detect the PFOA and the PFAS. And normally, for this method, the detection limit can reach to nanogram per liter, actually, which is pretty low. However, this method is still suffering some limitations, like offsite require offsite analysis and the time consuming and the high cost in the environmental monitoring. Yeah. So one option that we can shift to is the electrochemical impedance method. So the reason why this method can be used to detect the PFAS are based on two facts. The first one is that it has a strong absorption and interaction. A strong absorption and interaction mechanism exists between the PFAS and the nanoporous metal organic framework materials. According to these two papers, that they found that the sulfur atoms, of the PFAS polar head, actually they have very strong affinity to the metal center of the MOF materials. And then the second factor is that we know that the electrochemical impedance spectroscopy is one kind of rapid and sensitive detection method that is based on measuring the impedance changes at the electrode and the solution interface. So therefore, we're thinking that maybe after the capture of PFAS, the surface of the MOF materials will be changed, and then this finally will result in the change in the charge transfer resistance from the solution to the material surface. So therefore, in this case, we can use the EIS method to detect the PFAS concentrations in different water samples. So therefore, to find a suitable electrochemical platform that can integrate these materials into the platform and successfully use the EIS method is very important. Yeah. Well, considering right now that the mostly used planar interdigitated device has the problem of limited electric field penetration. So the penetration of the planar interdigitated device, the penetration of the electric field equals to the width of the electrode digit and the gap of the electrode between the electrode digits. So which means that most of the captures that about this active detection area, all these captures, all the changes cannot contribute to the final signals. So in order to keep the structure advantages of interdigitated layout while have an enhanced electric field penetration. So in this work, we propose this new no planar interdigitated microelectrode microfluidic electrochemical platform. And from our console simulation, we found that compared to the planar one, the channel of our no planar device is filled with enhanced and uniform electric field. While the electric field intensity in the planar device, you see, actually the intensity is almost negligible, which is to 0. Yeah. Okay, so the figure A is the picture of our final device. Yeah, actually our device has three layers, top and the bottom electrode. and the middle channel layer. So in this case, the MOF material was firmly trapped between the top and the bottom electrode in the channel layer. So this is the top view of our device. And we found that most of the MOF material can be used in our device, like CRML11, FEML11, and FEML100 that can be, integrated into our device. So here is the packing protocol, just to show to you guys how we get the final device. So in this case, instead of using the PDMS to form the channel, we here use one adhesive double-sided adhesive tape layer. So the function of this tape is first it can work as to bond the top and bottom electrode together, and then second it can be cut with a certain pattern, and then we can use it as the channel. So the use of this tape can greatly save the efforts to build the device. And then once we get this channel, and then the suspension MOF suspension solution is loaded above the electrode. And then once the material is dried, then the cover layer of the tape was peeled off. And then we use the top electrode to cover the whole channel. And then that's the device we get. And finally, we can use a pump, to pass the target solution through the channel, of course, through the materials, and then the signal will be collected using this impedance analyzer. So as I mentioned, above, we think that after the capture of the PFOS, this will result in the change in the charge transfer resistance from the solution to the material surface. So in order to analyze the changes in the charge transfer resistance, so here we propose one possible equivalent circuit for our no planar system. So in this circuit, the RS means the resistance that comes from the outside. CC is a double layer capacitance. RC is the resistance of the material and the solution. RCT is the charge transfer resistance. So actually, we just need to focus on the changes in the RCT. The Q and the W are actually constant element. So here is one work. That we published in the journal ACS Applied Material and Interface. In this work, we use CRML11 as the sensing materials. Here is the way how we treat the material and how we run the experiments. And the sensitivity of the device is defined by the resistance distance, the distance in the resistance, and divided by the initial resistance, which is resistance before the capture of PFOS. And in this work, finally we can get a detection limit about 0.5 nanogram per liter. Yeah. And here is a schematic diagram just to show how we run the experiments. So here is the material, MOF material, and this is the electrode. And once the target solution to pass through the materials, and then the PFOS molecule will be captured. And finally, all the changes in the charge transfer resistance will be collected and analyzed using the impedance analyzer. And for the actual water samples, actually all the processes are the same. We just need to change the solution to the water samples. Okay, so here is the work I'm doing right now. Yeah. So in this case, we have 3 water samples that both of them have different PFOS and PFOA concentration. For example, for the groundwater, it has the highest PFOS concentration. Well, for the landfill, it has the highest PFOA concentrations. And here are the EIS response. And finally, we found that for the groundwater, it has the highest response. Regardless, the landfill has very high PFOA concentrations. So actually, this result can demonstrate that the system, our system that based on the CRML11 and the non-planar device can show actually very excellent selectivity just for the PFOS molecules. And except the CRML101, we also other, materials for the detection of these molecules. So yeah, so that's our final goal, to our final, goal to find, the best materials, for the P40 detection and maybe for the near future use. Yeah. So that's all the work I'm doing right now. Yeah. So, well, sorry. The summary, yeah. So in this work, novel electrochemical detection system that based on the MOF and the non-planar device for ultra-sensitive determination of PFAS is proposed. And in order to, understand the working mechanism of our non-planar device, so one equivalent circuit, is proposed to understand the whole system. And then, so the COMSOL simulation, we found that our non-planar device can have an enhanced and uniform, electric field distribution in the fluid channel, in the channel. And finally, a detection limit of around 0.5 nanogram per liter of PFAS is obtained based on the CRM-L11 and our non-planar device. And then finally, I need to thank Dr. Elaborator from the PNL. Actually, all the materials that are used in this work is from their lab. Yeah. So yeah, that's all my work right now I'm doing. Yeah.
Great, thank you very much.
Yeah.
We have a few minutes for questions. If we
do have one. Are these sensors reusable? Can this be expanded to detect other PFAS compounds?
Actually, right now we just tried the PFOS and the PFOA. We didn't try other PFAS molecules right now. Yeah, but that's the work that we are going to do. In the next semester. Yeah.
Great.
I haven't tried that yet, but yeah, we will try that in the near future. Yeah.
Any other questions in Whova, Janice?
Yeah,
Oh.
not in Whova, but we did have one more in Zoom. Could it work in the gas phase?
I don't know. We didn't. We haven't tried that yet. Yeah, but I think maybe it can be used for the gas sensing. They reusable. Yes, we can reuse the device. Once the detection is done, then we can dissolve the whole device and then reuse it again.